All right, let's dive right into the heart of pretty much any modern chemistry or biology lab, the spectrophotometer. Now, this isn't just a machine. It's our window into the invisible world of molecules. It's how we can actually measure and quantify things we can't see, turning even the slightest hint of color into hard, solid data. You've probably read the theory in a textbook, but this explainer is all about getting hands-on, turning that book knowledge into real-world results. So, here's the real question, right? You can probably rattle off the Beer-Lambert law, but can you actually apply it? Can you walk into a lab, sit down in front of one of these, and pull off reliable, publication-quality data? That's what we're going to focus on today, closing that gap between knowing the theory and truly mastering the instrument. So, where do we start? Well, before you even think about preparing a sample, you have to think about the instrument's environment. This is where precision begins. Getting clean, reproducible data isn't just about how good you are with a pipette. It starts with a perfectly controlled, professional setup. This is about making sure the machine performs at its best and, just as important, keeping you safe. Now look, these points on the screen, they are not just suggestions. They are absolute must-dos for data you can trust. That 100 millimeters of clearance for the cooling fan, that's critical. If it overheats, the electronics will drift, and your baseline will start wandering all over the place, totally ruining your measurements. The detector inside is incredibly sensitive, so you have to keep it away from things that create electromagnetic noise, like a centrifuge. It's all about getting a clean signal. And yeah, you even see earthquake countermeasures on the list. A pretty serious reminder that in a pro lab, you have to plan for everything. And that brings us to a huge point about your personal safety. If you're working with, say, volatile organic solvents or anything hazardous, a fume hood isn't just a nice-to-have, it's a core part of your setup. Proper ventilation is absolutely non-negotiable. Seriously, think of it as essential safety gear that stops dangerous vapors from building up. A spectrophotometer is a powerful tool, and like any powerful tool, you've got to use it in a safe environment. Okay, so the physical setup is solid. Now, let's talk software. In a regulated professional lab, keeping your data safe and sound is everything. You just can't have people accidentally or intentionally messing with validated methods or deleting critical calibration files. And that's exactly why modern instruments have a really robust user control system. This table lays it all out perfectly. It's basically like the permission levels on enterprise software, but with scientific integrity on the line. You'll notice everyone can perform measurements, of course, but look at the restrictions on the operator. They can't delete files or change key parameters. This is so important in a regulated lab. It stops someone from accidentally wiping out a standard curve or tweaking a method that's already been validated. And only the administrator can touch the core system program, which makes sure the instrument stays consistent and traceable over time. The system also gives you some really crucial flexibility in how you handle your data. You've got options. You can save it to the built-in memory for quick analysis, you can pop it onto a USB drive to work on it elsewhere, or you can save it to a network for proper archiving. It might seem like a small thing, but that kind of flexibility is essential to how a modern lab actually works. All right, so the machine is set up and secure. Now, what can we actually do with it? Well, a modern spectrophotometer is no one-trick pony. It's more like a versatile analytical toolkit with different modes designed to answer very specific scientific questions. Let's just do a quick tour of this toolkit. Photometric mode is your basic workhorse. It gives you a simple absorbance reading at one specific wavelength. Spectrum mode is where you find a compound's unique fingerprint. It scans across a whole range of wavelengths to create a curve. This helps you find the lambda max, the wavelength where your substance absorbs the most light, which is key for getting sensitive measurements. Quantitation mode then uses that lambda max to build a standard curve so you can figure out the concentration of an unknown sample. Kinetics mode is super cool. It tracks absorbance over time, letting you literally watch a reaction as it happens. And finally, you've got built-in biomethods for common stuff like DNA or protein assays that just make routine work so much faster. But here's where things get really interesting. This is where the machine goes from just a measuring device to a real powerhouse of analysis. You see, getting the raw data is only half the battle. These machines have a whole suite of data processing tools built right in, and they let you uncover insights that are often totally hidden in that initial scan. Think of this menu as your command center for that deeper analysis. Right from this screen, you can run some pretty complex calculations on the data you just collected, which saves you a ton of time you'd otherwise spend exporting it to another program. Let's dive into a couple of the most powerful ones. So first up, derivative spectroscopy. Now, why on earth would you need this? Well, imagine you have a sample with two different compounds, and their absorbance peaks are so close together that they just look like one big wide hump on your spectrum. By calculating the mathematical derivative of that curve, which is basically its rate of change, the instrument can actually tease apart those overlapping signals and show you two distinct peaks. It lets you see things that were completely invisible before. And the cool thing is, you're in the driver's seat here. As you can see on the screen, you get to set the derivative order, first, second, and so on, and you can tweak the coefficient. This is a classic balancing act in science. A bigger coefficient will smooth out the noise, but it might also flatten the very peaks you're trying to find. True mastery is finding that sweet spot that gives you the clearest signal without losing the important details. Okay, on to the next tool in our kit. Here, we're choosing the peak area function. It sounds pretty simple, but what it does is fundamental for anyone doing quantitative analysis, especially in fields like chromatography. So why is this a big deal? Why not just measure the height of the peak? Well, the really crucial thing here is that this function calculates the total area under that peak. And according to the Beer-Lambert law, that total absorbance, the area, is directly proportional to the total amount of your substance. So this calculation is what turns a simple peak into a precise quantitative number. And this diagram really shows you how smart the software is. You can define a baseline, and it'll calculate the area of any peaks relative to that line. It can even handle peaks that dip below the baseline. That's what you see at A and C, as well as the ones above it, like B. It can even give you the total net area, which is D. It's a surprisingly sophisticated tool that gives you a ton of analytical power. So you've got all these amazing features, but how do you know the numbers are right? How can you actually trust what the instrument is telling you? That's where instrument validation comes in. And let me tell you, in any kind of regulated or quality-controlled lab, this is not optional. It is an absolute requirement. A good instrument will have automated routines built in that check its performance against major international standards, like the pharmacopoeias from Japan, Europe, and the United States. These are basically the official rulebooks for pharmaceutical quality. Running these tests gives you documented, traceable proof that your instrument is accurate. This is how you prove your data isn't just correct, but that it's legally and scientifically valid. And this whole process is built on an idea called traceability. You see, the quote here points out that this isn't just some abstract software test. It relies on real, physical, certified materials, like special optical filters that you get from standards bodies like NIST in the US. When you use these standards to validate your instrument, you're literally tying its performance to a global, unbroken chain of measurements. That is the very definition of good lab practice. All right, let's wrap up with something really important. What happens when the work is done? A true professional's responsibility doesn't just end with the experiment. It covers the entire life of the equipment, and that includes getting rid of it properly and safely. The deuterium lamp, the UV light source for the instrument, is a perfect example. You can't just toss it in the trash when it burns out. No way. As you see here, it has to be treated as industrial waste. It contains materials like tungsten and high-purity quartz, and it has to be handled by a licensed contractor following all the local laws. Knowing this is a fundamental part of being a responsible scientist. So, what's the big takeaway from all this? It's that a spectrophotometer is so much more than just a black box that spits out a number. Real mastery, from the physical setup and the user controls, all the way to the advanced data processing and responsible maintenance, that is the foundation that all credible scientific data is built on. So the only question left is, which of these features will you master next?